What if I told you that the most photographed black hole in history just revealed something that's making astrophysicists lose sleep? Back in 2019, humanity witnessed an unprecedented moment, the first ever direct image of a black hole. It wasn't a simulation, wasn't an artist's rendering, but an actual photograph of a supermassive monster lurking 55 million light years away in a galaxy called Messier 87. The image spread across the internet like wildfire, becoming one of the most iconic scientific photographs ever taken. But here's what nobody expected. 3 years later, the James Webb Space Telescope would turn its infrared eye toward that same black hole and discover something that's making astrophysicists lose sleep. The Event Horizon Telescope wasn't a single telescope. It was a global network of radio dishes connected together to create an Earth-sized virtual instrument. Scientists coordinated 8 observations across different continents, from Hawaii to Chile to the South Pole, and synchronized their data to create an unprecedented resolution. What they captured was the shadow of a black hole known as M87 asterisk, sitting at the heart of the elliptical galaxy M87. This black hole doesn't just casually exist in space, it's an absolute titan. We're talking about a mass equivalent to 6.5 billion of our suns squeezed into a region smaller than our solar system. The image itself revealed an orange-red ring of superheated gas glowing as it spiraled toward oblivion, surrounding a dark central region, the event horizon itself, the point of no return. The discovery was so groundbreaking that it earned the 2020 Nobel Prize in Physics, cementing humanity's ability to observe the universe's most extreme objects. But at that time, scientists were only seeing part of the story. Then came December 25th, 2021. After decades of development, setbacks, and a budget that ballooned to roughly $10 billion, the James Webb Space Telescope launched into space. Unlike its predecessor Hubble, which observed primarily invisible and ultraviolet light, Webb was specifically designed to see the universe in infrared, wavelengths invisible to our eyes, but incredibly revealing about hot, distant, and dust-obscured objects. Webb positioned itself at a special location called Lagrange Point 2, roughly a million miles from Earth, where gravitational forces allow it to stay relatively stationary compared to our planet. With a primary mirror nearly 7 meters across, Webb became humanity's most powerful eye on the cosmos. Scientists realized that while the Event Horizon Telescope had captured that iconic 2019 image, it had only been observing M87's black hole in radio wavelengths. What if they pointed Webb's infrared instruments at that same target? What would they see that radio telescopes couldn't detect? In 2023 and into 2024, the James Webb Telescope turned its attention to M87, and what it found sent shockwaves through the astronomical community. The discovery wasn't just interesting. According to multiple astronomers quoted in published research, it was very exciting. The telescope detected something shooting out from the black hole's poles with unprecedented clarity, the relativistic jets. But these weren't just jets. They were jets in infrared light, revealing structures and dynamics that had never been seen before. What Webb revealed was extraordinary. Streams of particles and energy being accelerated to near light speeds and ejected far into space, traveling thousands of light years from their source. The jets themselves became visible in fine detail, showing complex magnetic structures, regions of intense particle acceleration, and evidence of energy being released in ways scientists were still trying to fully understand. The infrared observations essentially gave researchers a new dimension to the M87 story, one that complemented but also expanded upon everything the Event Horizon Telescope had shown. To understand why scientists were so excited, you need to grasp just how remarkable these jets actually are. Around the black hole, magnetic fields don't just randomly exist. They get twisted and amplified by the rotation of the black hole itself and the turbulent motion of infalling material. According to current theories, the rotation of the black hole acts like a cosmic engine. Material spiraling inward heats up to millions of degrees, and the magnetic fields threading through this superheated plasma begin to channel energy outward. Some of that energy gets concentrated along the black hole's poles, and suddenly, instead of all the matter falling inward, some of it gets launched outward at velocities approaching 99.9% the speed of light. These aren't gentle streams. They're torrents of electrons, positrons, and possibly heavier particles traveling across incomprehensible distances. M87's jets are among the most powerful in the entire observable universe. They extend for thousands of light years, meaning they've been traveling for thousands of years and still haven't stopped. When particles moving at relativistic speeds collide with the intergalactic medium, they produce X-rays and gamma rays. They create shock waves. They heat surrounding gas to extreme temperatures. James Webb's infrared observations revealed the magnetic field configurations in these jets with the precision that ground-based radio telescopes simply couldn't achieve. Scientists could now see where particles were being accelerated most violently, where magnetic reconnection events were occurring, and how the jet structure changed at different distances from the black hole. But the jets aren't the only story Webb was capturing. The telescope's infrared sensitivity revealed the accretion disk surrounding M87's black hole in stunning detail. This is the rotating disk of material that's actively falling into the black hole. At the innermost edges of this disk, temperatures reach millions of degrees. Gas atoms are stripped down to their nuclei, and the extreme heat causes the disk to emit intense radiation, particularly in infrared and X-ray wavelengths. Webb could detect the subtle variations in temperature across the disk, seeing how material heats up as it gets closer to the event horizon. What was particularly revealing was the asymmetry. Due to relativistic effects predicted by Einstein's theory of general relativity, the side of the disk moving toward us appears brighter than the side moving away. This relativistic beaming had been theoretically predicted for decades, but seeing it confirmed in such detail in infrared light provided powerful validation of our understanding of extreme gravity. The accretion disk observations also showed variability, meaning that over time, the amount of material falling in, and thus the brightness of the disk, changes. This variability holds clues to the stability of the accretion process and how black holes feed on their environment. Additionally, Webb's infrared data revealed subtle details about the disk's composition and structure that had been hidden to previous observers. Here's where things get truly profound. Each new observation of M87 isn't just satisfying curiosity, it's actively testing our most fundamental theories about how the universe works. When James Webb observed those jets and that accretion disk, it was essentially performing an experiment in real time. General relativity, Einstein's theory of gravity, makes specific predictions about how objects behave near black holes. It predicts the size of the shadow, the asymmetry of the accretion disk, the relationship between the black hole's spin and the jet power. Every time these predictions match observations, it strengthens our confidence in the theory. But it's not just about validating Einstein. Understanding M87's black hole helps us understand active galactic nuclei, supermassive black holes that power some of the universe's most energetic phenomena. Many distant galaxies host similar jets. By studying M87 in detail, scientists are essentially studying a nearby example of processes happening throughout the cosmos. The jets from M87 may also play a role in regulating galaxy evolution itself. When a black hole ejects material at near light speeds, that energy heats the surrounding gas and can actually prevent new stars from forming in the galaxy. Understanding how this feedback mechanism works has enormous implications for comprehending why galaxies look the way they do and how they evolve over cosmic time. Furthermore, the particle acceleration occurring in M87's jets may be responsible for producing cosmic rays, high-energy particles that reach Earth from space. If scientists can understand how M87 accelerates particles, they're potentially solving one of the universe's enduring mysteries. The James Webb discovery isn't just a one-time observation. It represents a shift in how we study black holes. For decades, radio telescopes dominated black hole research because black holes emit powerfully in radio wavelengths. But Webb demonstrated that infrared observations reveal details that radio telescopes missed. This opened an entirely new avenue for research. Already, Astronomers have plans to observe other black holes with similar precision. Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, is next on the agenda. Unlike M87, Sagittarius A star is closer, brighter, and more variable. Observing it with Webb could reveal even more intricate details about black hole behavior. Beyond Webb, next-generation X-ray observatories under development will add yet another perspective. When you combine infrared, radio, X-ray, and other wavelengths of light into a comprehensive multi-wavelength picture, you get far more information than any single telescope could provide. Scientists are also coordinating observations with gravitational wave detectors like LIGO. When two black holes merge, they produce ripples in space-time itself. By connecting gravitational wave data with electromagnetic observations from telescopes, researchers can piece together a complete understanding of these catastrophic cosmic events.